Uh, this is the last part of lecture 27. We're going to discuss how CMB and anisotropy can give information about the geometry, spatial geometry of the universe, and in particular, the evidence for a flat universe. Remember, we said angular power spectrum of CMB and anisotropy can fix the cosmological parameters, and for example, the curvature signature K we see to be is equal to 0. We show that in the flat universe, the characteristic size of temperature structure in a CMB is about 1 degree wide. So the power spectrum peak at multiple number of L equal about 200. So first we start to find out what to determine the size of the temperature fluctuation as evidence for a flat universe. Following the first detection of anisotropy by the COBE satellite in the early 1990s, there were several balloon-based CMB experiments. In particular, the collaboration of Boomerang and the Maxima detected the CMB fluctuation on a smaller angular size than COBE's angular size, quite a bit smaller than the 1 degree resolution. The observation produced evidence for a flat universe. Here is a picture of the COBE CMB and anisotropy, and here the Boomerang. The point that so you see that resolution is much less than one degree. Because that's important because the character size of CMB temperature fluctuation in flight universe is about a degree wide. So if you want to see this, you have to have a resolution better than a degree. If the universe had any curvature, it would have distorted the observation, the observed picture. The CM radiation had been traveling uninterrupted since the universe was young. For when the photo decoupled time is 380,000 years, much less than the 14 billion that we're talking about. So therefore, the great distance it had traveled make the CMB an ideal probe of the geometry of the whole universe. Okay. It turned out for a positive curvature would have focused the CMB rays, making the anisotropy scale appear larger, and a negative curvature would have had the opposite effect, causing the CMB rays to diverge and shrinking the apparent scale of. Here is sort of some sense of cartoon. Here's what you expect for a flat universe. For positive curve and negative curve, the convergence and divergence of light ray would have distorted the anisotropy pictures. So in box 10.2, we calculate the CMB angular horizon in a flat universe. In the early universe, before photon decoupling time, the gravitational clumping of baryon was resisted by photon radiation pressure. So this set up we call baryonic acoustic oscillation of compression and replication, which gravity provides the driving force and radiation pressure the restoring force against the background of dark matter fluctuations, which are not subject to electromagnetic radiation pressure and thus start to grow much earlier. The photon baryon fluids can be idealized by ignoring the dynamic effects of the gravity and the baryon because the photon number density is so much greater than baryons. This leads to a sound wave speed. Remember, sound wave is the square root of pressure over density. So now if this mainly taking the photons, then the pressure, the radiation pressure is raised to one third of the radiation density. So P is one third of rho c squared, so you get C over square root 3 as the sound speed of this photon barium fluid. The compression and rarefaction were translated through gravitational redshift into temperature and homogeneity, as we talked before. By this careful analysis of the temperature and anisotropy in the CMB, we can garner much information about the early universe. We will see the flat geometry will imply the first peak at the sun horizon is a co-moving distance r. The sound wave would have traveled from the beginning of the universe to the decoupling time. So because since here is the co-moving frame multiple scale fact, this the proper distance, which in some sense you can parameterize as the sound wave speed times the time interval. So therefore, when you integrate, divide by a both sides and integrate r to get the sun horizon, and again we take the sound speed to approximately constant, so therefore dt over a. Now for a universe with flat spatial geometry, such horizon length, okay, our sound horizon on the surface of the last scattering will appear as the angular anisotropy of the size angle. The arc length divided by radius is the angle. Okay, so this if you want to say this is the radius of the scattering last surface, which is a sphere centered on us, with the radius big R, and divided by the arc length. That's give the angle. So R big R sub t is the co-moving distance between us and the last scattering. Okay, so which can be just like this, but now it's traveled by CMB light. So c, and from last scattering to us to time now. Okay, so since this is the sound wave, so the maximum, the horizon, the maximum distance of travel, the sound will travel. So this theta sound horizon, but then be the maximum angular size of density fluctuations. So this maximum, this is maximum. To evaluate these integrals, which goes for simplicity, assuming it's a matter-dominated universe throughout the whole period of time. So therefore, the scale factor a goes like t to the 2/3 power. Even prior to photon decoupling time, we can do that because the matter radiation equality, remember the radiation dominant switched to matter dominant at the matter radiation equality time, which is about 72 kilo years after Big Bang, compared to 380 kilo years after the Big Bang for the decoupling time. So it's not terrible, bad approximations. So now if the t goes like if a goes like 2/3, so t goes like a. So I invert this relation 3/2. So dt is a square root of a times dA. So you plug this in and divide by this a in the integrand, so you get a minus power, and that's good. So since a 1 over a is 1 plus 2 plus z, so square root of a is 1 over square root of 1 plus z. The z is redshift. So the angle size ratio of the horizon distance divided by the radius of the last scattering surface, and so the first thing to go here by this approximate is sound wave speed multiplied 1 over z of at last scattering, and this is equal to 1 over z of the redshift now, of course, that's 0, minus 1 plus z at last scattering. So this one, but this number is 1 over 1,000, so therefore this is very small correction, so we can ignore this one. So the denominator here is just 1. And the CS over C is just 1 over square root 3. And here is just, I just copy this numerator over. And in fact, this redshift at decoupling time is about 1,000. And we'll plug this in, and we just, you get 0.017 radians, which translates into about a degree. This 1 degree translates into the minimum multiple number, because remember we said the for large Legendre polynomial, the L number can relate to the passing by pi, the peak at the pi over the corresponding angle. So therefore, if we plug this in, basically put this result into here, you get pi and it's over 180. So thus in a flat split, we expect the first peak of power spectrum to be located at the multiple number about 200. Okay. Because realistic calculation, in fact, is L sun horizon about 225. So we just call the round number 200 because a very rough estimate represents a simplified calculation. So now, so we say the flat geometry implied the first peak at 200. So in fact, there is a peak at 200, and so we claim this evidence for flat geometry, flat spectral geometry. Because this represents the fundamental baryon sound wave traveling from beginning universe until the photon decoupling time. Now this seen 14 billion years later, now a blob this size will cover about a degree in the sky. If the spatial geometry of the universe is flat. Okay. If a positive curved case, positive curvature would have focused the CMB rays. So here is a cartoon, it's two-dimension pictures. So the flat space represented by a flat gray disk, and the positive curves be represented by the surface of a sphere. So if we same angle alpha, if the flat space corresponds to a linear length of lambda, would have been correspond to a small, for positive curve, be a smaller number. Okay, so therefore that's when by focused ray versus non-focused flat universe. So in a universe with positive negative curvature, the observed angular size would be different from, so therefore the L value would shift away from 200. In fact, we observe 200 because it's evidence for flat universe. Okay, here are the lessons from lecture 27. The cosmic microwave background is not perfect uniform. The primordial density unevenness is brought about by implied there was a baryonic acoustic oscillation, and that produced anisotropy. At 1 part in 1,000, there's a dipole anisotropy. That's due to peculiar motion for our local group of galaxies. And 1 part in 100,000, the multiple anisotropy can be thought as a baby picture of the universe when it's 380,000 years after the Big Bang. Statistical study of angular power spectrum, because you have theory of different parameters. So by fitting the observation, you can fix the cosmology parameters. So this is the main tool of quantitative cosmology. The fact the first peak at 200 means the spatial geometry of the universe is flat. k equals 0. As a remember, how interesting if k equals 0 also corresponds to total zero energy in the energy balance equations. Okay, the kinetic energy just cancels the potential energy part. In next lecture, which will be starting with chapter 10, we'll talk about inflation cosmology. The standard Big Bang theory, the Friedman, the Material, Robertson, Walker, is actually a theory about the aftermath of the Big Bang. It says nothing about the underlying physics of the primordial explosion itself. It gives not even a clue about what banned, what caused it to ban. So the inflation universe theory, on the other hand, is a description of the band itself and provides plausible answer to these questions and more. So that'll be the next chapter 10.